Welcome back for a second example of finding a determinant of a 3 by 3 matrix using the diagonal method. To set up the diagonal method, we want to form a 3 by 5 arrangement of elements using the elements from matrix A. So the first three columns of the 3 by 5 arrangement will be the same as matrix A. So we'll have 2, -1, 0, -3, 6, -2, and 4, 8, 1. The fourth column will be the same as the first column, so we'll have 2, -1, 0, and the fifth column is the same as the second column, so we'll have -3, 6, and -2. Now that we have our 3 by 5 arrangement, we're ready to find the determinant of matrix A. So we can use this notation here as stated in the original question, or we can use vertical bars like this to show the determinant of matrix A. Using the diagonal method, this determinant is going to be equal to the sum of the product of the diagonals from the upper left to the lower right, or these three diagonals, minus the sum of the product of the diagonals from the upper right to the lower left, which should be these three diagonals. So again, we start with the sum of the product of the blue diagonals, or the diagonals from the upper left to the lower right. So we'd have 2 times 6 times 1, that's 12, plus -3 times 8 times 0, that's 0, plus 4 times -1 times -2, that's positive 8. And then we're going to subtract the sum of the product of the red diagonals, or the diagonals from the upper right to the lower left. So we'll have 4 times 6 times 0, that's 0, plus 2 times 8 times -2, that's -32, plus -3 times -1 times 1, which is positive 3. So we have 20 minus, this would be -32 plus 3, or -29. Well, minus -29 becomes plus 29, so we have 20 plus 29, so the determinant is equal to positive 49. Now before we go, I do want to discuss some vocabulary. If the determinant of a matrix is equal to 0, the matrix is called singular. This means it is not invertible, or that it is degenerate, and does not have an inverse, such that A times A inverse is equal to the identity matrix. So again, if the determinant of the matrix is equal to 0, then A inverse does not exist. But in our case, since the determinant was equal to 49, that means our matrix does have an inverse that would satisfy this equation. Okay, I hope you found this helpful.